All right, so like what is a C2? Let's think about that, right? So you make the secondary alcohol. So where does it come from? All right, so let's see. All right, so we have, it's almost there, so but mind your nomenclature, right? So you have the right root, basically, it's going to be prop, right? So, but then we have the hydration. Some people say hydration, so will be used, right? So you need to use water in this case. And the correct guy is going to be 1-propene. Finally, so that's the one, right? So propane, so no, because it is an alkane, so you need to use an alkene. So you have like 1-propene. So just to remove the, what's that? You are going to remove the water, right? So OH is gone and H is gone. So that's it. So then if you draw the compounds, so like hopefully like draw will be easier, right? So if you're not asked to like name it, so but that's what you're going to have, right? So that's it. So it's going to be OH and H will be gone. So of course hydrogen will be removed from this carbon, right? So we remember that they are going to be kind of like removed from the adjacent carbons, right, in case of dehydration. So here you encounter the situation when you have like many various ways to remove the like groups of atoms, but that's how kind of the reactions decided to go, right? According to like some people. That's literally what one person said. That's how the reaction decided to go, right? So yeah, let's just go with that statement. And then, yeah, we know that we're going to remove OH and H from the adjacent carbons. And then you're going to have 1-propene. So if you remove OH and H like this, you get a double bond. If you remove the hydrogen from here and OH from there, then you're still going to get the same compound. 1-propene will be made, right? So that's 1-propene. And now finally, we are going to take a look at the previous compound relative to 1-propene. So here we go, right? So it's going to be compound number 1. So if we are going to make a propene, right? So where do we get it from? So yeah, essentially, so that's going to be the alcohol, right? So alcohol dehydration will give us the alkene, right? And then here it happens to be like fine with us, right? So let's take a look at this compound. That's exactly what we have in our question, right? So CH2, CH2, CH2OH, right? So that's the one. So here you have a couple things to eliminate, right? Such as H is eliminated, OH is eliminated from your adjacent carbons of the alcohol, right? So now you are going to make your alkene, which will be 1-propene, right? Or propene is okay to call it this way. So because there is no other ways to kind of like place the double bond and name it, right? Correctly. So 1-propene. So yeah, this can be derived from the primary alcohol. So again, here you will have kind of like the reactions going like back and forth, basically. So this one will be the hydration process, right? So, or dehydration, you just use H2SO4, right? So the temperature will be relatively high, like 180 degrees Celsius. You are going to get the alkene. So then next process will be like when you go from C1 to C2, you do dehydration, right? So that's your like dehydration process, let's call it this way. So then second process, right? So like as you go from C2 to C3, you are going to do what? You are going to hydrate, right? This compound. Again, same similar conditions, right? So that's going to be the hydration reaction. So then finally, we're going to have the dehydrate. No, this one is oxidation, right? You can just add the oxidizing agent, right, signified as such, and you are going to do the oxidation of the alcohol, secondary alcohol, to make the ketone, right? So that seems like a lot of terms, but if we think about that, so like we ideally should kind of recall them at least somehow, right, after review and everything. And yeah, here we kind of like recycle them just, but with new compounds, right? So that's like all that is. So then let's see what else we have next. So these are like multi-step reactions. So now we're going to get back to like simpler stuff a little bit, right? So it's going to be the ethers here. So for our intents and purposes, so the ethers will be like relatively straightforward, right? So which they are in general. So yeah, because we cannot make that much stuff from this combination of atoms, right? So that will constitute the ether functional group. So for ethers, we're going to have this kind of like a COC situation, right? So that's what we need to find out in our molecule, right? So you can see those two lone pairs, by the way, on the oxygen in a kind of completely new compound relatively, right? But some things, again, are getting recycled, right? So maybe next time you look at that somewhere, let's see what you can find out based on your current knowledge, right? Maybe lone pairs, maybe some kind of like single or multiple bonds, right? So stuff like that. So then we're going to take a look at some example ethers and then try to name them. Right, so we need to name each alkyl group attached to the ether oxygen alphabetically, right? Followed by the word ether, right? So here we have our alkyl groups, right? Or maybe it's going to be an aromatic group as well, right? Not necessarily we're going to have alkyl, but for this course, it's going to be typically alkyl substituents, right? So here we have ethyl, then methyl, this is CH3 technically, this guy is isopropyl, right? So then we have the famous phenyl and CH3 or methyl again. So let's take a look. So diethyl ether, right? So because we technically have a ethyl ether, so diethyl, right? So di again is a Greek term for two, and then that's going to be like used here to signify that we have two ethyl groups, diethyl ether, right? So then alphabetically comes next because we have two different substituents, methyl and isopropyl, right? So apparently they will be like that. So like iso here for the name of the substituent, right? So because like isopropyl in this case, they're kind of melded together, right? So you cannot just like, separate them. So because you don't have the propyl, right? You have isopropyl. So iso is named like as we saw in the chart back in the day, is the name of the substituent, right? So that counts alphabetically. Like we need to when we count the alphabetical order, so we need to count I, right? So like we need to understand that the name of isopropyl starts with I, not P, basically. That's what I want to say, right? So that's part of the name, not the count of like groups, right? So just like here. So iso, I, then we have methyl, IM, right? Alphabetically. Isopropyl, methyl ether. So that's how this like what this name sounds like. So finally we have like a couple groups here, right? So one of them is phenyl, starts with a P, not F. The other one is methyl, right? In blue. So let's see what happens. Methyl, phenyl ether, MP, right? So that's our alphabet order, and that's it. So methyl, phenyl, ether. And then, yeah, so you can find out, so maybe for your practice, so if you have some time, I don't know, like if you just sit in the library or something, write out the, what's it called, expanded structures, right? Show all the bonds. So this will be helpful. So you will kind of like, solidify the case that, okay, well, I know how to find ether group, like for exam purposes, for instance, right? So that could be helpful. So now we're going to take a look at like further details, right? A little bit like higher levels. So these are so-called partial charges, right? So that you can see on this diagram and the dotted lines, right, which represent the bonds existing between the molecules, right? So of ethers in this case. So in this situation, we're going to see this delta minus and delta plus, right? So on oxygens and carbons respectively. So here we need to like think about, okay, it's like what's the reason here, right? So because this will help us in the future a little bit. So like with other partial charges, right? So delta stands for partial, right? Plus or minus, that's the charges kind of like types, right? So and then so why what is the reason for those partial charges, right? So like what's the GenChem reason basically that makes carbon delta plus and then oxygen delta minus. Let's think about that, right? So there's a question in the Google Classroom once again. So what's the reason, right? So that they become all of a sudden delta plus and delta minus. Or maybe you can think about this way when you take a look at O and H, right? So like some of you did show that last time in their presentations, so to speak here, right? So I think it was Megan potentially who was showing like delta plus on H and delta minus on the oxygen, right? So that was like literally done by your peers, so like pretty inspirational with different colors as well, right? So, but now here we have like this situation happening with other atoms, right? So carbon and oxygen. So it is like, yeah. So, but principle is the same, right? But the atoms set is a little bit different. So you have carbon and oxygen now. Like, what's the reason, right? So we have some responses going in. So yeah, good job, good effort, I would say first, right? So let's get to that. So and then people say basically like very succinctly that it's going to be the electronegativity, right? So, and then some people say, so that you will see which atom lost or gained electrons. Yeah, this will happen later a little bit, right? Right now, you don't have the breakage of the bond. That's why there are partial charges, right? They will become full once they are like broken. And then, for example, just think about the case of dissociation of water, right? So that's where you have partial charges before ionization and you have full charges after ionization of water. You should always be able to kind of draw dissociation of water and carboxylic acids like at will. So, right. So when you're asked that, you do that. All right. So because of the electronegativity. All right. So now let's take a look at that case, right? So that's the situation. Carbon is less electronegative than oxygen. So consequently, oxygen will be drawing, right? Not just kind of like gaining electrons right away, but it will be drawing the electrons towards itself. It will become partially negative. Like carbon will become partially positive. So now finally we get to activity number 1, right? Which will be showing, right? So here you have hydrogen bonding. So yeah, you'll have the hydrogen bonding. It's going to be a little bit different, right? That's what we saw in the past on Thursday last week. So here you have ether of your choice and water, right? So like pretty like Gen Chem style. So, but we kind of like need to show the partial charges and then H bonding with dotted lines. So if you did some kind of like home prep for that, so maybe you're already good to go. So, but yeah, again, we'll give way to new people to try that so that they can experience the drawing on the document under the document camera at least once maybe this semester. So we still have like the full blown month of April, right, until the end of the semester, but now it is still March, right? So next week will be the last week of March. All right, so we have one candidate. So let's see. Yeah, you can go. So activity number 1 is taken. So let's see what happens, right? So you have the paper here and colors, right? So yeah, you can choose whatever you want. All right. So now let's take a look, right? So we have the ether and like a water. Yeah, maybe let's move it a little bit so that yeah. Okay, great. So all right, so like ether is being drawn, quite exciting, all right? So and the water molecule as well. Okay, that's quite a dotted line, so that's good. So all right, so we have delta plus and delta minus, right? So just to be proper, add the hydrogens, yeah, in whatever way you want. You can do the expanded or condensed structure, but again, so I'll say it once again, right? So and time, so don't just drop, right, things and then go away. Maybe lone pairs, right? So because I think it was part of the question as well. Okay, good job. And then the water, right, also has lone pairs. right? So the oxygen on the water molecule. Okay, yeah. So I think that's well done. So yeah, that's what we are going to have in this particular example, right? So delta plus on the H, delta minus on the oxygen, so they will connect and make the hydrogen bonding, right? So here you have all the conditions. You have the OH bond in the water molecule that will fulfill the conditions for H bonding. So you have the oxygen, right? So delta minus on the ether, and then you have kind of like this situation. Like one more thing, right? So just like you were seeing here, just show delta plus on the oxygen. I mean, on the carbon, right? So that's like, yeah, no big deal. So, and yeah, so then maybe you can show here delta minus as well, delta plus, right? Even though they are not explicitly engaged in this scheme, but they can theoretically bind to another ether molecule, right? Because you don't have just two molecules in space, right? So you have like Avogadro number of them, right? So yeah, just something to keep in mind. Okay, well done. So this is our answer, like for this piece, right? Hydrogen bonding in ethers. It needs to be specified with something else, right? So since they cannot hydrogen bond with one another, so they will need to be able to hydrogen bond with other molecules, such as water, or maybe some sort of like carboxylic acid, by the way, right? So that could be the case, or alcohol, right? So diethyl ethers. So let's just like some real life applications, right? So diethyl ether, so it looks like that. So here you have dimethyl, by the way, dimethyl ether, two methyls, right? So, but if you have this diethyl ether like this, so this is a common solvent, by the way, and can be used, I assume, somewhere in medical practice, right? So for those of you who are going to get to this like medical pathways. So this is going to be DEE, diethyl ether, right? Very common abbreviation. So maybe you don't remember now, so but maybe sometimes it will like show up and then you will like recall this, right? So diethyl ether, a couple ethyl groups. So the common solvent in like chemistry and could be used also like I guess in medicine. Maybe not, who knows? So anyway, so now we're going to finally get to switch to the new class of compounds, and then it's going to be the thiols, right? So previously, so if you recall, right, or just pay attention, right? So we were looking at this guy, right, and how it's made, right? So we used to have the H2S, hydrogen sulfide, and then we kind of like can make by just breaking the bonds, right? Break this bond, all right, or technically this one, whatever they are the same, and then switch H to isopropyl, make a thiol, right? So some random thiol, right, with your favorite like R group, as some people started using that already. So now what happens? So now let's take a look at some details, right? So again, we try to kind of like connect some knowledge areas, right? Such as like organic chemistry versus like general chemistry, because apparently like these days it's like popular, right? And could be like the way for the future, kind of like think about like different knowledges and how they're connected, right? So maybe this will be like useful for you as well in like whatever you want to do with your life, right? So after after this stage. So now let's take a look at the thiols, right? So that's what they look like. So yeah, basically we are going to have the SH group, which again, so if you want to reduce your like level of anxiousness looking at this new compound, just think about this as a derivative of H2S, right? It's much simpler molecule to like deal with. But if you, let's say, can manage H2S, then you can also manage this compound in like to some extent, right? So at least from the fundamental perspective. So what do I mean by this? So like if we think about this guy, right? So third butyl thiol, right? So where does it come from? It comes from H2S, right? As some people, several of you mentioned very wisely. So that's the one, right? So H2S. So H2S is what? So this is going to be technically an acid, right? So it is a weak acid. So it's kind of like close. If you look at sulfur, it's close to what's that? Chlorine, right? oxygen is close to fluorine, so they would have those kind of like acidic properties conceivably, right? So from just the periodic trends perspective. So also we know that this could be considered water but modified, right? Instead of oxygen atom, we have the sulfur. So if we know how the water dissociates, which we should or have to, rather, it's going to be something like this, right? So you have the oxygen, right? So, and then if I tell you like dissociation of water, right? So you can do that with just like one molecule or maybe with two. So, but anyway, so if you do it like with one molecule without the hydronium ion formation, right? Which like technically should be done. So you're going to have what? You're going to have this. So now we're going to have more lone pairs of electrons on the oxygen, right? So because this blue lone pair decided to move to the oxygen, right? So we can show it even with the curved arrow. So the lone pair now will reside, this like blue pair of electrons used to be shared, now it's not shared, right? So it's on oxygen, and then oxygen gains an extra electron also technically, becomes negative charge, right? Negative charge on the oxygen. And then also we're going to have here another one, right? Which is going to be H plus. So that's what happens. So now let's take a look at another molecule, right? So this is going to be H2S. So, and here we go, H2S. All right, so here we go. So that's going to be another structure. So sulfur. So if we take a look at the periodic table, so rather here we need to take a look at the fact that it is close to oxygen, right? It's in the same, what's that? Same column of the elements, and then it happens to have also a couple lone pairs here, just like that, right? So that's what the sulfur will look like. So it's similar to oxygen, right? So now, if I ask you, what about the dissociation, right? So, well, you can do it this way as well. So this bond will be broken. So we also, if we think about, have same things, so also pair of shared electrons, right? And then we can show that it's going to move towards sulfur like that, right? So now let's see what happens. So we need to like we need to make those both green, what's it called? Green dots reside on the sulfur, right? So let's make it happen. So here we go. We will go maybe like this way. So it's a little bit at an angle. So that's your equilibrium arrow. So some people use that, good for you. So then here you have it, right? So S, couple of those. So then you have something here. So that's going to be a question for you. And then you are going to have those, bless you, green electrons on the sulfur, and it needs to be like that, right? So negative charge, right? So now another question for you in the Google Classroom. So it's gonna be like that. Okay, so let's take a look what happens next. So next question is what else? What else needs to be there, right? So that's the question. So if you have this kind of process, right, which is going to be called ionization because you make ions, or dissociation because you dissociate a bond, right? So such as SH bond is broken here. So what else needs to be shown, right? So again, so some terms, right? Water can show acidic behavior, right? What is acidic behavior? That's when something loses H plus, right? So because of its structure. So now what about H2S? H2S used to be, well, it was also like known, it is known as an acid, right? So it can make salts, sulfides with, for example, what's that? Some like other compounds such as like sodium sulfide. It's going to be Na2S, by the way, right? So that's your like derivative of this acid, Na2S. So because you have here +1, and then sulfur will become 2-, right? So you have 2 plus and -2 becomes 0 charge. So that's a sodium sulfide. So it can be like used in I don't know, some applications, right? Whatever like it's useful for. So, but it does exist, right? So that's a sodium sulfide. So, and then it is a salt, right? So that is derived after the reaction, conceivably between sodium hydroxide and H2S, right? So, but now, so we established that, okay, H2S also should behave as an acid, right? So then consequently, what should be happening, right? So to make it the acid. All right, so we have the like effort here going on, right? So quite a bit of responses. Great. So thank you for doing that. And then we are unequivocally say that it's going to be H, right? So, but be careful here. Don't just say H, right? Because somebody will say, ah, like H atom. But in fact, it's going to be H, but with the plus charge, right? So be careful here. So because this, like whatever, let's say I'm going to like circle this in the red, right? So this is the H atom. That's just H, right? You can call it this way. It's going to be okay from the like, terms perspective. So this is the proton, right? So this is the atom, right? So even though it is bound to like the atom of sulfur, so this is still just an atom, right? Because it's H with a dot for one electron. So if you look at the periodic table, that's what the H atom is supposed to be, right? So just H with the dot. So now this guy, this atom lost its green electron, and now it's like this. So there's literally no electrons. So that's going to be called a proton, right? So that's another term. That's a derivative of the H plus, and it is a proton here. So, okay, great. So now let's take a look at, I guess it's the time for the next activity, right? Okay, great. So we need to show the ionization of a thiol of your choice with 5 carbons. So here we have the thiol with the third mutual, so it's a 4 carbons, right? So, but now at this point, you should be able to generate some sort of like 5 carbon chain, right? You have the freedom here. So maybe it's going to be alkyl chain. So maybe it's going to be like aromatic ones. So, and here you go. Yeah, I guess you can go. Let's see. Okay, somebody is already kind of like prepared. Good job. So here your color choices and take it away. All right, so let's see the dissociation of the thiol. Quite interesting. All right, well, a lot of expanded structure going on, so that's good, right? So yeah, the bonds, according to one of the undergraduate TAs, by the way, his name is John. He was with us last semester. He was saying, well, show the bonds to kind of like track your progression of the chemical reaction, right? So this is an example of the chemical reaction here. Wait a little bit, okay. And one more thing is missing. So you lost one piece, right? So it used to be SH, right? But then what happened to H?
Isn't it a lone pair?
Yeah, it's going to be on the right side, just like draw it on the right side. So yeah, you need to show the proton, right?
Isn't that right here?
Yeah, use this like anion and then say plus H plus, right? So and now yeah, that's literally all it is, right? So yeah, that's great. So that's well done. So you just again like a reminder, right? So I guess I can just use it like all the time, infinitely. So so here, yeah, that's your like initial what's it, compound, right? So you can call it a reactant, right? So if you're completely like at the loss of terms, just say, well, it's reactant. Why? Because it's on the left side. So this is the left side of this arrow. So this stuff is like on the right side. So this is the arrow, right? All proper. Good job. So you have your counter ion, awesome, with all the like lone pairs and everything, right? And then just show like the product, right? So don't just like stop at the biggest structure and then leave it, right? So yeah, it's gonna be like helpful. So for example, if you, let's say, I don't know, like go to Stop and Shop and buy 4 avocados and some sort of like mineral water, you just kind of like pay for that, right? You take 4 avocados. and you just don't leave like mineral water at the what's it called, at the cash register, right? So like same thing here. So don't leave out H plus in this situation. So anyway, so now let's take a look at like other things, right? So what's it? They are analogs of alcohol, right? So just like we were talking about like who came from where, right? So that's like another way to think about that. So because some compounds are analogs of other ones. So this complicated thing is also an analog of H2S, right? Technically, so because we just switch hydrogen to this huge, just like alkyl chain, right? So pentyl, it's pretty straightforward. It could be anything. It could be some kind of cycle. It could be phenyl instead of this, right? So with 6 carbons, yeah, if I tell you like 5 carbons total, like make a phenyl because phenyl contains 5 carbons. I mean 6, right? We'll still be kind of like fulfilling this at least condition. So then they are non-polar relatively, right? So because the electronegativities are close in this case for carbon and sulfur, right? So if we take a look at just the periodic tables, so oxygen will be a little bit more electronegative than sulfur, right? So sulfur is a bigger atom substantially, so it will have less tendency to draw the electrons because it's surrounded by a bunch of electrons, right? So it's like 8 versus what's that? So we go from 16 atomic units, right, to 32. So it's pretty significant difference. All right, so now it also can form disulfides. That's what they will look like, right? So yeah, basically for disulfides, for now, we just need to keep in mind that we are going to see this combination, right? So SS will be in the middle, and then R and R prime will be some sort of, for example, alkyl groups. Maybe R will be methyl, R prime will be ethyl, right? So that's going to be your simple example of a disulfide, right? So they're derived from thiols. So now let's take a look at the chemical reactions. So here we go. So this is going to be just a generic chemical reaction. So here, so R stands for some sort of functional group. You might think about this as a like random functional group, but typically for the cases of organic chemistry, it's going to be some sort of like what's that, organic group. By the way, so this is your famous activity number 3. So if you look at this situation, so that you can consider this piece, this huge piece, as a RSH, right? So that's your like random functional group. So now apparently thiols, so like easily undergo this oxidation reaction, right? So just like we saw it with alcohols, but they're going to form not ketones, but disulfides that will look like that, right? So now let's take a look at what happens, right? So these are your beloved circles with the colors, right? So here you go, right? So like that's like hopefully shows us what happens, right? So maybe even show the electrons, right? So even better. So there used to be green electrons on sulfur, maybe yellow electrons on the hydrogen, right? So it becomes like an like Irish flag or something like that. So you have that situation, right? So the hydrogens are like removed upon the oxidation process, and now you have those green liberated electrons on the sulfur, right? So if you were to explain it to like one of your peers or a buddy, then you'll be able to do that, right? So just show those electrons here, right? So that's where they end up. So because we, for the moment, have some kind of a separated sulfur, metal sulfur pieces, right, with their free electrons, but then they will be able to like make a bond, right? So because for the covalent bond, we just need to have like one atom with a free electron and another atom with a free electron, and then they will be connected. So to make a bond, right? So SS bond in this case. So if you think about maybe you form, let's say, you have the like OH with the free electron and hydrogen with the free electron, right? So then they will form a bond and then they will make water. So here, same principle, right? So you make just a sulfur single bond. That's what you might call it, right? And then you're going to form some sort of like disulfide. So that's what we'll call those compounds for now, right? So then we can go backwards, right? So apparently the opposite of oxidation is reduction. So in this case, H, right? So it will stand for the reduction process. And this will basically tell you that we are going to increase the number of hydrogens in the final molecule, right? So if you think about it, so what's going on here? So let's see. So this bond will be broken, right? So then it will be hydrogenated. So hydrogen will be added here. So you are going to go from RS pieces, which are, let's say, in green, here to RSH, right? So you are going to form two RSH. So that's your balancing, right, of the equation here. So since you have disulfide, you have two pieces here, right? So then you're going to make two smaller molecules from one, right? So some kind of particular examples. So that's the one, right? So you have methyl, sulfur, sulfur. So then this compound is a disulfide, right? So you're going to reduce it. So what's going to happen is that those presumably green electrons will be separated, right? So the SS bond will be broken, right? So that's one action that happens. So then you are going to have the source of hydrogen, right? So which is going to be introduced upon the reduction. So because as you correctly said last week on Thursday, so what's reduction, right? So it could be considered as the increase of the hydrogen atoms. And here you have the increase of the hydrogen atoms. So they are now added to sulfurs, right? So with their, let's say, blue electrons or something, right? So you make either way a covalent bond, SH and SH, right? And you have two of those pieces. So now you have two thiols, right? So disulfide made a thiol, right? Made two thiol molecules from one. So basically, it used to be maybe 2A, and now you have A and A, right? So that's just how it went. If you think about this from some kind of general perspective, right? So then next reaction, right? I think it's going to be the ultimate ones, so that we might encounter, right, with various thiols. What could happen is the reaction with a heavy metal ion, right? So typically, so it is a double charged one, right? So that's one feature to pay attention to. So this is going to be a 2 plus. So metal with a charge of 2 plus. So M is just some generic metal. So now you have Hg2 plus. So that's what we'll typically see. Maybe we can also see some sort of other ones, such as magnesium potentially can also react, right? Because magnesium is 2 plus, right? So if you were to kind of think about that, then it is a possibility, right? So just kind of by the virtue of the charge, right? So that's where we're at right now. So maybe it's going to be calcium, right? Also famous ions. So if you look at the periodic table, so both magnesium and calcium are in the second column here. So they have the charge of 2 plus, right? Two second column, two charges. So and then what's going to happen is the following, right? So you are going to, let's say, theoretically remove those hydrogens, right, from your SH groups. And now you are going to substitute two hydrogens, right, with Hg2 plus, this guy. So then you are going to make new bonds, right? So basically, now each hydrogen used to be able to make one bond with the sulfur, right? So, but now you are going to switch from two hydrogens to one Hg, right? So because Hg is a double charge, right? So divalent kind of atom and can make two bonds, two sulfur atoms. All right, so then as a result, you will also have here, so the what's that generation of two H pluses, right? So yeah, that's what we will have in mind. So because technically, why is that so, right? So if you have Ag2 plus, this kind of mercury with a double charge, right? So your peer just showed us that you are going to have this kind of S minus on the thiol, right? So then in that case, it's going to be very well explained, right? So why does it happen? Because if you have, let's say, if you think about H2S, right? So H2S molecules. So it can dissociate, and then it will give you SH with a minus and H plus, right? See, I kind of did not forget the H plus here. So then if I'm going to somehow like get like Hg 2 plus, right? And then I'm going to react it with SH minus, right? Like so. So here to make a proper compound, right? To make it neutrally charged, I'm going to have to use two SH minus anions. So now it's going to be proper, right? So because it will give me Hg S or HS twice, right, in the formula. Why is that so? Because the compound, right, to be kind of like legitimate, it has to be neutral, right, before it can participate in any chemical reaction. So yeah, you can form like ions at some point, right? So they do exist as well. So, but if you want to make kind of like the stable compound, you want to minimize its charge, right? So then here you go, right? You will have Hg or mercury with a charge of 2 plus, right? And then you have the negative charge on each of the SH ions. But if you have two of them in the molecule, it's going to be the charge of -1 multiplied by 2 becomes -2. So +2 and -2 becomes 0. Total charge will be 0. That's what you are going to kind of ideally have in a stable neutral compound, which can like further be like used for chemical reactions, right? So that's exactly what happens in your like thiol case, right? So technically, so if you want to go in details, then you can say, well, there's going to be 2 plus charge here, -1 here on sulfur, -1 on this sulfur. And then here you go, right? You'll have a total charge of 0 on this like entire compound, right? It's going to be charge of 0. So, and then it'll be like a stable compound. That's what we're kind of driving for. So then what else? So now we have some time for further chemical reactions, I would say. So let's take a look at what we have here. So perhaps, I don't know, like what's interesting. So you have A, B, C, D. So which one do you want me to do? So just pick your letter. A. Okay, well, let's take a look at A, right? So this one is supposed to kind of what's it? Distract your attention, right? So and scare you a little bit. So, but yeah, it's okay. So here it's the topic is thiols, right? So that's why we're going to concentrate on the thiol piece, which is going to be the carbon SH, right? So here we have the oxidation. So sometimes it will be kind of like nudged, right? So just do the oxidation of the thiol in your molecule, right? So that's why you're looking for the thiol group, and then you'll be fine, right? So, well, but then you need to do like more stuff, right? So this guy in the blue, so in the blue circle, so you can literally call it like R for now, right? So, and then that's how you will kind of like minimize that like scariness of this group, so to speak, right? So what's going to happen next? You are going to do the oxidation, right? So go back to the next slides, right? How does oxidation happen? So it's supposed to form the disulfide. That's why you have two molecules of RSH originally, right? So what you're going to do is the following, right? So you can go down like a cheat pathway and then just do that like R. Then you're going to have S and then another like S and R, right? So that's it. So that's going to be your product, right? So if you don't want to redraw all those like atoms that constitute the R group. So if you want to be proper, right? So if you like don't make any assumptions, if you don't announce that the blue part will be called R, then you will have to redraw everything, right? But it's no big deal. So you're just going to be like that. So it's going to be HN3 plus, just kind of copy paste mode at this point. CH, COO minus, right? It's like ionized carboxylic acid or amino acid. We'll take a look at this later, right? So, but now we just need to be able to like literally redraw that blue piece, right? So then we're going to be concerned with the red one because that's where the bond is broken, right? The SH bond in particular. And then we're going to kind of like do the like mirror image of this like compound in the black font, right? So, or the part of the molecule is going to be S, then it goes down like CH2 here, then CH, and then we're going to have NH3 plus attached, and then this is going to be our like amino acid like piece like that. All right, so that's going to be your compound A. You are going to make nothing more than a disulfide, right? So you see the principles kind of like are recycled here. So, but you're just going to have like a huge different new molecule, right? So now maybe let's take a look at the compound at part C, right? So here we have again two molecules of the thiol of some sort and Pb2 plus, right? So that's an example of another heavy metal ion. It's not going to be mercury, Hg, it's just going to be a lead, right, in this situation. So, well, let's see what happens, right? So here again, we are going to break this like SH bond. So here you have the hydrogen, right, technically. And then you are going to continue. Okay, well, you're going to make H plus according to your peer, and then S minus, right? So it will be also happening in this molecule. So because of the sulfur like concentration, sulfur like focus, right? So we just have not like your peers group, right? But it's going to be like a different one, right? From 4 carbons, like no big deal. So, well, let's redraw that. So it's going to be looking like this. So we have sulfur with a minus, right? Technically, then we're going to put this Pb in the middle. And then another molecule of the same kind, just like flip it, right? For the drawing purposes. And make sure that you don't like forget your methyls and the CH2 pieces. So that's the one, right? So this one is 2 plus. So you have the bonds, right? So here we can show them as dashes between Pb and S because they apparently fall in the middle between like covalent and ionic bonds. But it's kind of going to be advanced topic. But for now, we just can agree that we can show them as bonds, at least like here, in terms of exams and stuff like that. So I guess that's the one. We'll continue. I mean, that's it. We'll continue with activity number 3 on Thursday. So take a look at that and be ready. Right. So, see. Bye, everyone.